I, Mrs. K.S. Gadgil, from Department of Electrical Engineering, AISSMS IOIT Pune, today will be discussing single-phase half-wave diode rectifier with R load. Let us first understand what is rectification. It is a process of conversion of alternating input voltage to direct output voltage. A rectifier converts AC power to DC power. In diode-based rectifiers, the output voltage cannot be controlled. A rectifier may be half-wave type or full-wave type. It can be 1 pulse, 2 pulse, 3 pulse or n pulse type. The number of pulses in a rectifier configuration is obtained as under. Pulse number is equal to number of current or voltage pulses during one cycle of AC source voltage. We will be discussing single phase half wave rectifier with R load. This is the simplest type of uncontrolled rectifier. It is never used in industrial application because of its poor performance. Its study is, however, useful in understanding the principle of a rectifier operation. In a single phase half wave rectifier, for one cycle of supply voltage, there is one half cycle of output or load voltage. As such, it is called single phase one pulse rectifier. Let us consider the circuit with our load. The circuit diagram for a single phase half wave rectifier is as shown. During the positive half cycle, the diode is forward biased. So this is the positive half cycle. During the positive half cycle, the diode is forward biased. Therefore, it conducts from 0 to pi. During positive half cycle, the source voltage is equal to the output voltage, or you could say that the output voltage is equal to the source voltage, and the load current I0 is equal to V0 upon R at omega t is equal to pi, right? At omega t is equal to pi, V0 is 0, V0 has become equal to 0, and for R load, the current is also 0. As soon as Vs, that is the supply voltage, tends to become negative after omega t is equal to pi, the diode D is reverse bias. It is therefore turned off and it goes into the blocking state. The output voltage as well as the output current are 0 from omega t is equal to pi to omega t is equal to 2 pi. After omega t is equal to 2 pi, the diode is again forward biased and its conduction begins. For a resistive type of load, the waveforms or the output current waveform has the same waveform as the output voltage. Diode voltage VD is 0 when the diode conducts. Diode is reverse biased from omega t is equal to pi to omega t is equal to 2 pi, right? Source voltage is assumed to be sinusoidal, which is equal to Vm sine of omega t. To find out the average value of output voltage, we have V0 is equal to 1 upon 2 pi integration of 0 to pi Vm sine of omega t d omega t. You take Vm upon 2 pi outside. Integration of sine omega t is minus cos of omega t. It goes from 0 to pi, which is equal to Vm upon pi. Similarly, to find out the RMS value of output voltage, you have V0R is equal to 1 upon 2 pi integration of 0 to pi Vm square sine square omega t d omega t whole raised to half. So is equal to Vm 1 upon 2 pi. Integration of sine square omega t is written as 1 minus cos of 2 omega t upon 2. And if you solve this integration, you get RMS output voltage is equal to Vm by 2. Then average value of load current. Average value of load current is what? I0 is equal to V0 upon R. V0 is what? Vm by pi. So you get I0 is equal to Vm by pi R. Similarly, RMS value of load current is equal to I RMS is equal to Vrms upon R is equal to Vm upon 2R. Peak value of load or diode current is Vm upon R. What is peak inverse voltage? Peak inverse voltage is an important parameter in the design of rectifier circuit. It is the maximum voltage that appears across the diode when it is in the blocking state, right? So if you see from the waveform, when the diode is in the blocking state, whole of the voltage, supply voltage appears across the diode, and PIV is the peak inverse voltage, it is the maximum voltage. So what is the maximum voltage? Maximum voltage is Vm, which is equal to root 2 into Vs. What is Vs? It is the RMS value of the secondary transformer voltage or transformer secondary voltage, right? So Vs is your transformer secondary voltage. Then next is your output DC power, which is PDC is equal to V0 into I0. What is V0? Average voltage into average current. So Vm by pi into Im by pi. Then output power is your PAC is equal to, you have your RMS voltage into your RMS current. So it is Vm by 2 into Im by 2. So Vm Im by 4. Then you have rectification efficiency, which is equal to PDC upon PAC is equal to Vm Im upon pi square into 4 upon Vm Im. So it comes out to be 4 upon pi square, which is equal to 0.4053, which is 40.53%. Then form factor is defined as the RMS value of voltage upon the average value of voltage. So if you substitute the values for RMS voltage and the average voltage, it comes by pi by 2, which is equal to 1.5708. Then the next term is the voltage ripple factor, which is under root of form factor square minus 1. So substitute the value of form factor, you get 1.5708 square minus 1, which is equal to 1.211. Since the source voltage is a sine wave, we have taken source voltage is equal to sine wave, which is Vs is equal to Vm sine of omega t. You have its RMS value as Vs is equal to Vm upon root 2. Then load current is the same as the source current. So RMS value of source current is RMS value of load current. We have found out the RMS value of load current is equal to what? It is equal to Vm upon 2R, or it is, Im by 2. Then VA rating of the transformer, right? It is equal to what? Vs into Is, which is equal to Vm by 2 into Im by 2, which is equal to Vm Im upon 2 root 2. Then to find out the transformer utilization factor, you take a ratio of the uh, DC output power upon the VSIS, or the VA rating of the transformer. So if you substitute, it comes out to be equal to 0.2865. That is for a load of 100 watt. So if you have a load of 100 watt, what is the transformer rating you will require? You divide it by 0.2865, which is equal to 349.6 VA would be required. Then the peak value of the source current is ISP is equal to Im. RMS value of source current is Im by 2. So crest factor is the ratio of peak value upon the RMS value, which comes out to be equal to 2. So this is the working and the performance parameters of half wave rectifier. I have tabulated the same. So you have DC output voltage as Vm by pi, RMS value of output voltage as Vm by 2, voltage ripple factor as 1.211, rectification efficiency as 40.53%, transformer utilization factor as 0.2865, peak inverse voltage is Vm, crest factor is 2, number of diodes is 1, and ripple frequency is F. So with this, we come to the conclusion of a single phase half wave diode rectifier with R load. Thank you.